Thank you so much, Yash, for accepting the invitation and uh, uh, volunteering to, what do you say, spend your valuable time and sharing the knowledge,
Of
your
course.
knowledge with the researchers and the viewers of SciTech Talks. Because the main viewers of this SciTech Talks are always the beginners who are getting started in the field of computer vision and looking for a lot of ideas. So with that
Yeah.
in focus, we will have our discussion with a list of questions, uh, which will be mainly focused towards that and helping those kinds of researchers. Of course, there are a lot of other viewers also who would like to understand more about your expertise. Okay. So, to get started with, can you please introduce yourself first, and can you please tell us some motivation on why you wanted to get started in the field of computer vision? Yeah.
All right. Yeah, sure. So, as you know, I'm doing my PhD at the University of Oxford currently
Yeah.
with the Visual Geometry group. And here I'm advised by Professors Andrew Zuckerman, Andrea Vidaldi, and Joao Henriquez and Irolina. So I have four advisors. And it's a long story why I have four advisors, but we can talk about that later. And what I'm working on in my PhD is 3D computer vision and deep learning. And my main focus is 3D reconstruction with object centric learning. So I want to reconstruct scenes in an object centric manner, and I also want to learn the dynamics of scenes. So if you have just a video of a scene where objects are moving, my goal is to reconstruct that scene in 3D but across time. So it's like a 4D reconstruction of that scene. That's what I'm working on now. Before I joined Oxford, I was a senior researcher at Qualcomm AI Research. So Qualcomm is a company which mainly works on hardware and uh, technology related to communications, but they also have a AI research division which works on edge computing. So their main goal was to develop AI algorithms which could be deployed on device, on edge devices and in a very constrained settings like low power, low memory settings, and so on. So my work there was mostly on deep learning in such constrained settings, and I worked on lots of algorithms like quantization, compression, architecture search, and some of my projects were related to 3D computer vision, but most of them were mainly on the architecture side of things. So how do you design deep network architectures which are suitable for such devices? So that was my work at Qualcomm, and we published a few papers there, a few patents too, during my 2 years of stint there. Before that, I did my master's at the University of Michigan, Ann Arbor, in computer science, and even before that, I did my bachelor's in IIT Bombay in electrical engineering. So I had a long journey going from India to US and back to UK, and now I will be going back to India, in a few years. So
Okay. Okay. Okay.
yeah. And
So
the second question,
is your ultimate, what do
hmm,
you say, goal go back to India and into one of the IITs, or how is it?
well, academia is an option I'm keeping open, but
Uh,
at least for now, my inclination is towards industry. So I would like to go into industrial research, but
hmm.
like the goal remains the same. I want to like devote my talent, my hard work to India, and I want to work in India in the future.
Okay. 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 Yeah. But it's an interesting thing, right? So you went to US and came back to UK. Generally, a lot of people whom I know actually they tend to settle back in US and they look for options in US. Uh,
Yeah,
is it is it because of Professor Andrewsism and you came back to UK?
kind of. So
Okay, okay.
the long story short, when I was in the US, um, since my goal was to come to India, I am well aware that in India, if I want to be in research, then you need a PhD, which is a bit unfortunate, because nowadays in the US you can do a research role without a PhD also, and
Mm-hmm.
especially if you're working in AI. But that's not the case in India yet, right? So
Mm-hmm.
I wanted to get a PhD, and I applied for different PhD programs, and one of the programs I got accepted to was Oxford. And as you said correctly, I was very fortunate that VGG was the group I will be working with in Oxford. So it was a no-brainer that I should come to Oxford and work with Professor Andrew, Andrea, Joao, all these great people here.
Mm-hmm. Okay, okay. And how was because I know Professor Andrew Zisserman from the days when I took this course on multiple view geometry in computer vision. And I didn't had the fundamentals of linear algebra when I took that course. Of course, I was simultaneously, and in the next semester I took the fundamentals of linear algebra.
Yeah.
So it was quite challenging to understand that course, but at the same time, it was interesting. The way he has written the book was so good that it really helped me really big time in following that book. And so, how was your experience of working with Professor Andrew Zisserman?
Yeah, it was pleasantly surprising, I would say. So I have worked with professors before I came to Oxford, and
Mm.
those were also very big shots. And usually, we all may have the same experience. Like if a professor is very, very famous, they're very big,
Yeah,
then they would
yeah,
have less time to devote to a student, and it would
yeah.
be a bit difficult for the student to, pursue their PhD under such professors. So my
Okay.
bar was that. When I came to Oxford, I thought, okay, Andrew also is like a huge person in computer vision, then obviously he won't have any time for me and so on. But I was actually pleasantly surprised in a way that Andrew is a person who is extremely kind and down to earth, and he will give you all the time you need for your successful PhD. And interestingly, he knows, not interestingly, actually, it's kind of obvious, he knows more about your field than you do. So if I'm working on a very
Mm.
specific problem, I am supposed to be devoting all my time to that. But even though I do that, Andrew always knows something more, and he always give you something insightful in the meetings. And uh, he has a small notebook always in the meeting, and he's taking notes all the time about what you're saying.
Mm.
And
Mm.
it happened once when I was submitting to CVPR last year, and I forgot about a few action items I was supposed to do, over like 2 weeks.
Mm.
And Andrew came back to the meeting, and Andrew was like, "Hey, Yash, did you do this, this, and that?" And I'm like,
Mm.
"Oh, I forgot about that," but Andrew remembered. So it was a bit. It's great. It's great working with him.
Yeah, yeah, good. His talks used to be very crisp, and it used to be very, very interesting. I
Yeah,
know he works quite a lot on 3D, but at the same time, he has significant work in
yes,
video activity recognition as well. So the
yeah,
the last time I presented my work at NCV at Hubli, and he was a keynote speaker there, and it was really interesting to listen to his talk.
it's true. Yeah.
Yeah, yeah. Glad that you got into his. I think very few get there, but I'm happy that you made that thing to join his group.
Like, I'm also very grateful for that. Yeah.
Yeah, yeah, good. So you have done on edge devices. You worked on edge devices in Qualcomm AI, right? But this is something different what you are currently doing. So was there any specific reason to make that shift or transition, or do you see some connectivity between these two topics, or how is it?
So there was a reason I chose 3D as my topic for PhD because when I was working in Qualcomm, I worked really intensively in the field of edge computing. I published a lot, and that was my main focus basically. But
Mhm.
when I worked in the field, it kind of felt that the field of edge computing as a research area was being saturated. Lots of papers
Mhm.
that come out in quantization compression, but as a long-term goal, it wasn't a field I would choose for research. It was going more
Mhm.
towards production and less towards research. And it
Mhm.
got me thinking, what is the field of research that will last for the next 5 years? Because if I'm doing a PhD, the field should be such that it has some relevance after I finish my PhD for a few years, right? And 3D was an upcoming field. It has been there for a long time, but especially in the era of deep learning, not a lot of things have been done in 3D. Most of the work has been in 2D and multimodal side of things, maybe on videos of it. But there are some papers on point clouds and meshes and so on, but not much, right? And that was one of my things I realized when I was working at Qualcomm, because some of the projects I did there were on 3D. Like I did a paper on 3D handful estimation, and I just realized that there is so much to do in 3D computer vision and
Mhm.
in terms of research, and there are many unsolved problems. If you think about edge computing, that's also a big thing, right? Because most of the architectures you use in 3D computer vision are huge. They are very heavyweight 3D convolutions. Maybe if they use 2D convolutions, even then they are quite computationally intensive. So there's a big scope of research for how do you make these architectures more resource efficient. Apart
Mhm.
from that, there is also a lot of work required in how do you even represent 3D data. So nerf has become a big thing nowadays, but even then people are still struggling to find an appropriate way of
Mhm.
representing 3D data. So that's also one thing I'm exploring right now. But in general, I think it's a very interesting area right now if anyone wants to do a PhD in computer vision. because all the applications coming up in the future, like AR, VR, or even in medical imaging and other things, autonomous driving, they all need some exposure to 3D computer vision. So
Mm, mm, mm.
very lucrative area to be in.
Yeah, yeah, good. You said as the field of edge computing is coming to saturation and the scope here in 3D is a lot. But please correct me if I'm wrong, because my experience of dealing with the edge devices is quite limited. But from what I understand is, say, if you want to deploy some complex models like transformer-based models onto edge devices, is quite challenging because of the number of computations it performs. So, how can we use these complex models onto these edge devices? Suppose say you have 3D itself. What kind of state of the art approaches are there to deploy these 3D based processing onto edge devices?
Yeah, I think that's a good question. So most of the work I did was before the Transformer era, and like before
Mm,
2020, it was not that famous yet. So all the algorithms I developed were mostly for CNNs, and I realized that for transformers, those things don't work. Like for transformers, for example, if you want to quantize the weights or activations, they're all dynamic, right? They're not in CNNs the weights are fixed, but in transformers the weights are depending on the current layer. So you would do the value query, and then you'll get the weights, and you multiply with the queries again and values again and get the output, right? So
mm,
what happens is that there are some papers on quantizing transformers, and they show that the activation distribution you get is quite strange compared to CNNs. It's not very nicely behaved. You get some bimodal or multimodal distributions in the transformer activations, and if you have multiple modes in the distribution of activations, it becomes a bit difficult to quantize them because you can't use the same bins that you had for CNNs to quantize the activations of transformers. So as a
mm,
whole, I think it is quite challenging nowadays to quantize transformers and deploy them on edge devices. And they themselves are quite resource intensive because there are some works on linear time attention, but mostly it's quadratic time. And all these transformers are huge in size. So you can't really deploy them on like edge devices. So I think in short, there is scope, I think, in research of how do you actually make them efficient and how do you deploy them. And so when I said it's getting saturated, I meant that from the algorithm side, it's getting saturated. But there's a
mm,
lot of work still required in the hardware software co-design because when you deploy deep learning architectures on hardware, what hardware you're deploying to is also important, right?
mm,
Because every different device has different kind of hardware architecture, and depending on that, you should design your deep learning architectures to best utilize them. So I think that part of research is very important, but sadly, most AI researchers don't have experience in hardware and vice
mm,
versa. So you need someone who is knowledgeable both in hardware and software to make the most in this area. So I think if someone out there listening is interested in both software and hardware, I think this is the a really interesting field for them to work in.
yeah, yeah, yeah. That's an interesting point you made. It's like just because uh, transformers are hard to deploy on edge devices, but it doesn't mean that it's not possible. But transformers might need a different kind of an hardware architecture than what is there today,
Yes.
so that they are also more suitable to the edge devices. Yeah.
Yeah.
Yeah, good. Good. Thank you so much for sharing that point. I think that's very useful for everyone. Uh, Good. So, coming to some of your approaches, right? So, what kind of edge devices you mainly used in Qualcomm AI? So, because are these like, did you validate all of your approaches on mobile edge devices, or were there any standard other platforms where you have validated your approaches?
Some of the algorithms I developed were for general purpose hardware, so they were not really restricted to any like special hardware. Uh, for example, I had a paper on LSQ plus, and there was one more paper called LTP, which is learn threshold pruning, which was for model compression. So these two algorithms were kind of general, and they could be applied to any architecture out there, which did not, which was hardware agnostic. But internally in Qualcomm, obviously we had developed a lot of architectures for hardware, and we call them hardware accelerators for AI. So
Mm.
Qualcomm is really a great place where lots of hardware experts develop these AI accelerators, and it's a bit confidential to talk about what exactly those were like. But
Okay.
what I can say is that yes, the work we did in Qualcomm was both. It was a bit general purpose so that we can deploy these for customers and others can use it too. But some of the work we did was proprietary, and which was meant for the in-house accelerators and in-house stuff that we did.
Okay, okay, okay. I understand because working with company, it's always we cannot talk about it in the public
Yes.
forums. That's perfectly all
Yes.
right. So, were your patents were also related to these hardware? Uh, what do you say? These kinds of techniques?
Yes,
All, yeah.
absolutely. So some of them were about hardware software co-design. So how do you design accelerators which were suitable for like such algorithms? And some of them were about the algorithms itself, like how do you quantize, compress these models and make them resource efficient. So both of them.
Mm-hmm. Yeah, it's quite interesting to understand to tailor your algorithms according to the hardware uh, or modify the hardware itself, which is more suitable for the software that you're trying to design. Yeah, it's a
Absolutely.
strike a balance is something quite interesting. Yeah.
Exactly. There's a conference called TinyML. I think you may have heard about it.
What is
So
it?
it's
Sorry,
a TinyML. So tiny
Tiny
machine
ML. Yeah,
learning.
yeah, yeah.
Yeah. So it's a very interesting conference, and I had the fortune to attend one of the in-person conferences before the pandemic in San Francisco. So all the people from NVIDIA and Qualcomm, all these hardware companies come there together, and everyone's developing their own, own type of hardware accelerators and so on. And we got the chance to talk to all these people and what the work they were doing. And it is so interesting to get the insights from them about exactly what you said right now is, oh, we have this accelerator in-house. Let's say I'm talking to a person from ARM, and that person told me that we have this accelerator and it has so and so memory requirements and it has so and so components. So how do we design an algorithm that is suitable for this hardware? And one of the things very important that people don't realize, and what I learned when I was at Qualcomm, is that when you when your goal is to have a very low latency model on any hardware, people mostly think that, oh, the if the model is very huge, it will be very slow, and the size of the convolution layers or the amount of multiplications additions it requires determines the speed of the architecture. But that's not true. What we found out was the most important bottleneck in the inference time of any model was the data IO. So how much time does it take to write the activations to memory and load them from the memory when you're doing the forward pass of an architecture is actually much more costly than the actual multiplications and additions you do in the architecture. So people need to think about how to design hardware architectures which make this data IO extremely efficient, which will in turn lead to lower power consumption and lower latency in their models. So these are the interesting things which you learn when you're in industry and not in academia, because
Hmm.
well, you also learn in academia, but I think it's a biased opinion because I learned this in industry myself, that you get to look at these things and experience these things in person, like hands-on in industry.
Hmm. Correct, correct. I was about to ask about the same point when you were talking about TinyML, right? So, one of the projects that I was working on when I was at University of Lincoln. So initially we thought, okay, moving to NVIDIA edge devices like AGX or N will solve our purpose because it had a higher GPU memory when compared to the GPU memory in the laptop. But it
Yeah.
seems to be that that specific edge device had a lesser bandwidth, data
Yeah.
bandwidth when compared to the data bandwidth on a laptop. And we were struggling, and initially it took time for us to figure out. But yeah, because that data bandwidth is also very crucial for which also contributes to the latency of the overall system, basically. Yeah, good. And so your works on this QKD, learnable threshold pruning, LSQ plus data-driven weights initialization, structured convolutions. So
Yeah.
some of them are edge agnostic, right? That's what you are saying. And
Yes.
some of them are like very specific to Qualcomm approaches.
Right.
Yeah.
Right. So all
Uh,
of my published work is
mm,
hardware agnostic because in
hardware.
research papers we can't really talk about the internal
Yeah.
hardware. That's why we had to be careful about what we publish in industry. But there are some algorithms out there, not mine, but let's say from Intel, there's a paper called TQT, which is I forgot the name. It's a while since I looked at this, but
Mhm.
TQT, IMQ, these are very interesting works, and these can be used for special purpose hardware. So not the hardware like GPUs; they won't work on GPUs as well as other ones. But if
Mhm.
you have some CPUs, then these might be useful.
Okay. Okay. Okay.
Yeah.
Okay, good. So from the coming from the 3D processing side, right? So you had couple of works recently on the 3D processing. So when I was going through it, I was also going through it. Maybe I have a couple of questions there on that side. So these days, a lot of people talk about nerves, right? So can you tell us in simple terms how nerves can be understood for somebody who is getting started in this field? Probably he must be aware of traditional epipolar geometry, some of the technical terms there, stereo geometry. Yeah, he must have understood. But how
Yeah.
nerves is giving a great value addition? Why nerves is so popular?
Okay. So first of all, nerve has become a very hot topic in 3D computer vision since
Yeah,
2019, since the first paper came out.
yeah.
And anyone who wants to get into this field now will have to read a lot of literature and get used to a lot of things before they can contribute something to this field. And I think I would advise if someone is doing a PhD right now and they want to explore nerve as their PhD topic, then be really careful about that. Think about if you really want to do that because, as Andrew says, his advice always is like to choose your topic carefully and to choose something which is where you can contribute meaningfully. Right? Your contribution
Mm,
will have some
mm,
impact. Anyway, given that, let me talk about what nerve exactly is. So nerve is basically a representation for 3D scenes. You have point clouds, you have meshes, different types of representation. You have voxels and so on. So all of these are more explicit representations. So in point clouds, you can explicitly manipulate points and you can move points and things like that. In meshes, you have triangles and faces and vertices and so on. So these are all explicit. But in nerve, it's more of an implicit representation. So what you're doing is for any point in the 3D scene, you are querying a model which gives you the density and color at that point. So you don't exactly have access to the density or color of that point, but you have to query it through a model which will give the information. And with that information, then the way they train nerves is if you have multiple images of a scene from different camera poses, then what you're doing is that you assume you have a scene model that you're trying to optimize, right? And you render the values for a pixel through that model. So you have a rendering equation, which is coming from a paper long back in computer graphics. So you have a physically plausible rendering equation, which takes the densities and colors and gives you the pixel color based on those 3D densities and 3D colors, right? And you know the actual pixel color now, so you can compare the
mm,
rendered color with the actual color and apply a loss to optimize that 3D model. So once you
mm,
do this with enough images and enough optimization iterations, you get a nice 3D model. And what you can do now is that with this 3D model, you can render this model from any view you want. So that's called novel view synthesis. So you can get
mm,
different views. You can actually render the scene from any view you want. So you can kind of do a fly through. You may have seen the videos where it almost looks like a drone flying through a scene because you just simulate the viewpoints and you render the scene from those viewpoints and you get a video of the scene as if you're walking in the scene or flying in the scene, right?
mm,
So
mm,
that's what Nerf is great at. It's great at novel synthesis. What people found out very soon was that Nerf is not very good at extracting geometry of the scene. So you can get very good, very high quality novel views, but you cannot get high quality geometry. Then other approaches came out. There's an approach called Neus, Neus, which was similar to Nerf, but the intention was to get accurate geometry. And after that, a lot of papers have come out. Like it's not the only paper. Like maybe 100 papers have come out on this topic
mm,
of how to get exact accurate geometry of a scene from a nerve. There's a very recent paper from NVIDIA called uh, Neural Angelo, I think.
mm.
It's a very impressive approach for extracting geometry from multi-view scenes. So I think that's the crux of nerf. And the interesting thing is that nerf was one of the first approaches to give such a high quality of novel view synthesis, because before that people used to use meshes and point clouds to render scenes. And with point clouds you have an issue of having holes in the scene, right? Because if a certain part of the scene or region of the scene is not seen from the point cloud, then if you render that part of the scene you will get holes, like you'll just have no information there. And the same issue with mesh. But in nerf you can kind of fill that area using interpolation because it's a continuous field and so on. But it also has its own problems, like it requires a lot of data, a lot of images to train the nerve. It can't work
Mm,
in few shot settings very well,
mm.
and so on.
Yeah, yeah. Thank you so much. I think a lot of online resources they talk about giving you technical details of nerves when I ask about what
Yeah,
is nerve, but I think you gave a very nice answer about it's an implicit representation of a 3D model, basically. Yeah.
exactly.
Good. Yeah, good. And recently, I've been also hearing about Gaussian splats. So,
Oh, yes.
right. So, how they compare with nerves? Do they come under what do you say, generating good novel view synthesis, or do they have an property of getting an accurate 3D model or geometry of the 3D model? Yeah.
So I just want to say like Gaussian spelling is so awesome. I've been using it for the last 2 months since it came out. And
Okay.
the main, I think the main up it has over nerve is that it's extremely fast to optimize. So it
Mm,
takes maybe a minute to a few seconds to optimize the Gaussian splatting model on a scene that you have.
mm,
It's very stable, and you can really control the model. So what I mean by that is that in nerve, since it's implicit, it's very hard to control the model because you have to query a network to get the densities, and it's very hard to visualize and so on. But in Gaussian splatting you have Gaussians. It's literally a point cloud with covariances at every point, right? So all the advantages you had in the point cloud where you could manipulate points and you could move points and so on, you have the same advantages in a Gaussian splatting model. But at the same time it gives you the same advantages that nerf has. It can give you high quality normal synthesis. It can give you a decent geometry. Geometry is still a problem with Gaussian splatting because the Gaussians you get after optimizations are not really at the surface of the objects. They can be inside the
mm,
object, they can be inside the object. So if
mm,
you just splatting the Gaussians that are optimized and try to extract the mesh from that, it might have some problems. But there are some recent works which have tried to overcome that, where they try to align the Gaussians with the surface, so using the surface normals, and then you can get a very accurate geometry from that. So I think it's a great tool to work with. It's very fast, so it helps you in the experimentation phase of your ideas and so on. And
mm.
since it is it gives you more control of what you're doing. And I think I have personally experienced that because I've worked on Nerf for a while, and now I have shifted to Gaussian splatting, and I can see
Mm.
the difference in what I can do with
Yeah.
this new.
Yeah, yeah. Sometimes these things looks crazy. The fast with the rate they are developing, it's quite
Oh,
challenging to catch up with these things. Yeah,
it's
yeah,
overwhelming.
yeah. Sometimes it's overwhelming. True. That's the right word. Good. And your other work on epipolar geometry, right? Because nerves is not my area of expertise, but epipolar geometry is something which I personally didn't really explore much, but this is something which I learned much during my course in multiple view geometry. Right, so it
Yeah.
looks interesting from the way it was developed, the idea was developed using it for image retrieval. Like so it looks really interesting to me. So what was the
Yeah.
motivation behind the using it's like where did the idea come from on how did you guys thought about using epipolar geometry as a cue for the image retrieval problem?
Right. So when I began the project, image retrieval was not really the main focus. The main focus was how do you incorporate geometry priors into transformers? Because the issue is that with CNNs have these priors inbuilt, right? They have the locality prior because they only look at the neighboring pixels to get the output and so on. So you have these interesting priors in CNNs which make them very effective at generalization and so on. But with transformers, the issue was that they lack any priors, and they are just really powerful learners. You give them lots of data and they will fit the data very well, even better than CNNs. The question we had was that, okay, that's great. But what if we want to generalize new scenes and we want to do cool things with that, like some geometry reconstruction, some retrieval, and things like that? Can we incorporate geometry priors into these multi-view transformers? Was the starting point, and retrieval was just a use case we wanted to showcase with, because we could not think of any other simple enough use case and which could effectively demonstrate the idea very well. In retrieval, the issue is that, let's say you have a teddy bear, right? And you look at the
Mhm,
teddy bear from the front, you have a view of the
mhm,
teddy bear, and now you look at the same teddy bear from a very obtuse angle, let's say like almost the back, but not the back, like some obtuse, like 120 degrees angle from the initial view. And you want to detect if the two views are of the same object or not. Now, as a human being, you can do that because you can say that, okay, I understand the angle is obtuse, and now given that the angle is obtuse, I can do some inferencing and some reasoning to get the output that, okay, it's the same object. But can
mhm,
transformers do that? And that was the issue here. So epipolar geometry is a very good way of representing 3D geometry, but in a very efficient manner, right? There are different ways of parameterizing like stereo geometry or 3D geometry. You can have actual 3D models, right? Like point clouds or meshes of the object, or you can have the fundamental matrix, or you can have depth and different things. But epipolar geometry has the same information that depth has, kind of, like not all of it, but in a way. But it is very nice to parameterize that. As we found in the paper, you can actually use the cross attention of the transformer to incorporate the epipolar geometry and kind of learn that patterns to do this reasoning in the inference time. So that was the main contribution here. There's one more paper, I think, from DeepMind, which did similar things to use epipolar geometry in the attention mechanism. And I think
mhm,
that's a very crucial thing, is that you should always think about the easiest way to parameterize things. And I think for 3D geometry, the easiest way to parameterize things is epipolar lines and epipoles, and all like fundamental matrices and so on. So
mhm. Okay, okay. I got it that point. And one last question I have, right? So we initially started with your motivation in 3D computer vision and Qualcomm. So it's like how was your experience at Qualcomm AI? And we talked about the hardware software, the need for hardware software co-design. That was very interesting, and we talked about the need for the data IO, improvement of the data IO among the hardware devices. And then you said about in nerves, Gaussian splats, and how you used epipolar lines. The final question of this podcast is like, uh, if somebody is getting started in the field of, say, 3D computer vision, or or contributing towards the edge devices, so contributing more on building algorithms towards edge devices. So what is your suggestions? Can you suggest some interesting problem statements for them?
okay, so I think one of the problems, as you said, is about designing efficient architectures for 3D computer vision.
Yeah.
Um, the issue with that is to define the problem. So I think you can have point cloud segmentation, object detection in LiDARs, and scans, and so on. So these applications require efficient architecture. So people need to think about how to do that, how to design efficient architecture for that.
Yeah.
And of course, before you start into any field, you have to read about the existing literature, and there's a lot in this case. The
Yeah.
second thing, I think, so the first thing I told was about feed-forward models. The second is more about reconstruction of images and so on, of scenes and so on. Sorry, and the essential problem nowadays is to do the reconstruction in few short settings. So if you have 50 images of a scene, you can do the reconstruction easily with a nerve and so on, right? But what
Mm.
if you have only a few images, like maybe 4 or 5 images of a scene, and you want to reconstruct the scene plausibly? So
Okay.
the problem of reconstruction from few short settings is interesting, and plenty of work nowadays focuses on diffusion models for this problem. So they are using diffusion for text to 3D, image to 3D, and so on. So people, uh, you know, uh, interested in this field should look at that and kind of think about if they can contribute to this field. Let's see what else. I think one of the issues is most of the scenes people focus on nowadays are object centric or very simple scenes with inward facing cameras. But reconstruction is especially challenging when you don't have inward facing cameras. When you have cameras which are, let's say you have an autonomous driving scenario where the car moves in a straight line, right? So the camera is moving in a only in a translation component. There is no rotation component there. So it
Mm-hmm.
becomes very challenging to construct scenes in those settings. So it would be interesting to explore this problem of how do you reconstruct scenes where you only have very little rotation component or no rotation component at all, or maybe if you have freely moving cameras. So egocentric videos is a big problem nowadays, because if you're working on VR, virtual reality, then usually you have the camera on the head of a person. And Meta is doing a lot of investment in this area of egocentric videos. So there's Ego 40 dataset which people can look at, or Epic Kitchens dataset which you can look at. So I think doing 3D vision in egocentric settings is very challenging, and there's a lot of unsolved problems here about how do you handle dynamic objects, how do you handle state change. So if you have Epic Kitchens, so a person is in a kitchen and doing lots of things. Let's say the person is cutting an onion, right? So the onion state of the object, onion object is changing. It was uncut and now it's cut, right? So it's
Mm.
not just that the object is moving or transforming; it's actually changing its state. So how do you handle this is very difficult, and I have no idea. But this would be very interesting to explore. Um,
Okay, okay, okay,
yes, some problems which people
okay.
are facing.
But you said that you are dealing with reconstruction of objects across time, but isn't it related to the state change that you're talking about? Yeah.
So I'm not dealing with state change. Like state change would be extremely difficult to handle.
Okay.
So I'm dealing with simple situations. So because these problems become very ill-posed if you don't put in assumptions, right?
Correct.
Um, so what I'm doing is solving dynamic reconstruction from monocular videos. Now, monocular video itself is quite ill-posed because you don't have enough views for every time step to reconstruct the scene at that time step, right? So you make some assumptions. You assume that the object is not moving too much, right?
Mm.
Because with that assumption, you can kind of have some regularization. You can assume that objects are locally rigid or they're completely rigid, and do things with that. So in the
Mm.
same sense, state change is a very big change. So without enough data or enough inputs, it would be very hard to model that. So you would need either segmentations of objects in 2D, or you would need some sort of information on what uh, state changes are possible, like maybe some priors from some pre-trained models or so on about state change and things like that to solve this
Okay.
problem.
Okay. How about having the, say, if we have something like a real sense camera, and if we capture the models across different time instance of a certain object, is it and the object changes its state at each and every time instant, or at least say maybe for every few time instance. So is it possible to register the models, and then can we capture the how the 3D model has evolved during this time period which we have captured? Is it easy to do, and is it to what extent this specific problem statement is explored?
I think it's definitely plausible because
Okay.
so you can have a model that learns these state changes. Like you can have a model which understands that onion can only change its state in a certain way, right? It cannot change,
Mhm.
cannot go into
Good.
steam or something like that.
Yeah.
So every object has some physically plausible or some realistic changes possible. So
Yeah.
it is possible to maybe train a model that understands these changes, and then you just plug in this pre-trained model into your reconstruction scenario and use that as a prior. I
Hmm.
don't think it will be simple though, because
Hmm.
first of all, you need a lot of data to do this,
Hmm. Hmm.
to understand what state changes are possible.
Hmm.
And it also needs a lot of object understanding and context understanding too, because um, how can I say this? Like the same object can have different state changes depending on the context of the scenario, right?
Okay.
So
Okay.
I would assume the model would need an understanding of what activities are being performed
Hmm.
to expect what changes would happen to the objects
Okay.
in
Okay.
context.
Okay.
Yeah,
Okay. And can you share some good reference, says in this context, what I just talked about? Is it possible for you?
yeah.
Um,
Sure, I need to find them, but So I don't know exactly about works which have dealt with state changes, but there are some very interesting works which have dealt with egocentric videos where these things happen. So I would
Mm,
suggest looking at Epic Kitchen's dataset, which is, as I said, a person working in the kitchen and they have a camera attached to their forehead and they record everything. So there are some papers which have developed reconstruction models on this dataset. There's a paper called Neural Diff from our lab. It's a very interesting paper and it deals with dynamic static separation in such videos. There's
mhm,
one more dataset called Ego 4D from Facebook, which is
mhm,
very interesting. And many papers have come out which solve different problems on this dataset. So it would
mhm.
be helpful to look at these papers too. In terms of state change, exactly, um, I need to look into it. But if I find something, I'll send it to you and maybe you can share with the viewers later on.
Okay, okay, sure. Because I've been looking at something like capturing the state changes since
I
my
see.
PhD, but I never ventured into it because if you see, there's something like if you're trying to, my research expertise majorly was in underwater imaging, and
Okay.
right, and during my PhD, and so but the task there was, can we really, when the object is there inside the water, and if the camera is there outside the water, can we really capture the surface of the water, how the water surface has evolved over the period of time? But water
Interesting.
is a transparent, right? So
Yeah.
that's the main challenge on can to capture the 3D reconstruction of the water surface. There are a lot of people who use this Navier-Stokes formulation and other things on how to capture
Right.
the flow of the water surface, but the state change, since then I was looking at, but never deeply ventured into it. So yeah,
Yeah.
that is the
It's
reason I
a
was asking you about it. Yeah,
right, right. But I mean, what you were trying to solve is even more challenging because
yeah.
water is transparent, and if you're using vision to solve this problem, then I can only imagine how difficult it can be. But kudos to you to even venture into this area and like approach it head on.
Yeah, because we were just keeping checkerboard at the bottom, and then we were trying to track how the checkerboard pattern is getting distorted, and
Right.
then used that was trying to use that as a cue in order to reconstruct the water surface at that time.
Very
But
interesting. Yeah.
yeah, that was only one problem statement I was just looking at, but never deeply ventured into it. But anyways, thank you so much, Yash, in spite of your busy schedule, just before going to Europe's.
Yeah.
So, in spite of your busy schedule, you spent your valuable time and shared your knowledge with us. Thank you so much for your time, and all the very best for your Europe's presentation. I know how prestigious being part of NeurIPS is, being a researcher in this field of computer vision. So I think I wish that you should make the best out of your presence in NeurIPS. And we would like to maybe, if possible, I would personally catch up with you in Oxford once and then try to understand more on what are your key learnings from NeurIPS.
Definitely. And thanks a lot for hosting this podcast and all the interesting questions. I think you're doing a great thing by doing this and making research more accessible to budding researchers like myself. And thanks a lot for having me on this. And yeah,
Great pleasure, yes. Yeah, yeah. I'll see you soon in Oxford again after you're back from NeurIPS.
absolutely, absolutely. All right,
Okay.
let's keep
Yeah.
doing this.
See you. Yeah. Bye.
See you. Bye.